Somebody's calling you.
It's going to be, they're calling me everything.
To propose you off first. Shall we start?
Yeah.
Okay, good morning, everybody. It's a pleasure to have today with us Teymoor Saifollahi from the Observatoire of Strasbourg. So Teymoor is originally from Iran. He's got his bachelor and master in Tehran on engineer and astronomy. And then he moved to the Netherlands for his PhD. And he got his PhD there in Groningen in 2022. Then after the PhD, he had a postdoc still at the Captain Institute until 2024, until when he moved for a new postdoc position in Strasbourg, where it now currently is. And is interested in galaxy evolution, in particular in dwarf galaxies, and is an active member of the Euclid consortium, particularly is co-lead of the local universe working group. And he has worked a lot on the early release observations. And today he will show some results about what about Euclid. And please, Teymoor.
Okay. Thank you, Francesca, and good morning, everyone. It's my pleasure to be here with you in this audience. And for that, I want to thank you for inviting me. It has been my long lasting plan to actually visit Bologna, but it never happened in the past. I think it's the first time I'm visiting Bologna. I know many people here work here, did studying here, master, PhD, or a postdoc at some point in their career. So I was always curious about this place, but at the end, I managed to come here. And I hope this continues, and there'll be other occasions that I will visit Bologna. So, yes. So today, and for the next, let's say 40 minutes, I'm going to tell you about global clusters of dwarf galaxies. I believe that there's plenty of potentials in understanding properties of global clusters of dwarf galaxies for understanding galaxy evolution, star cluster formation evolution, but also the nature of dark matter eventually. So, but also, as I'm going to show you, we don't have enough data and also good models to really explore these. That is kind of information we lack at the moment. And I'm going to cover most of the observational part in my talk today. But also, I will show you that this is the right timing to really start exploring global clusters of dwarf galaxies due to some upcoming observations, as well as next generation of simulations. So based on what I just said, I framed this presentation into 3 questions. So each question is quite general. I'm trying to address each question through the presentation and give you some brief answer for each one. Starting from the fact that why we look at dwarf galaxies and why we should care about the global clusters. Like what is that we learn out of this? And once it is clear to us, then it is about what we know already, mostly observationally, and what we don't know. There's plenty that we don't know. Actually, you will see that most of the things that we know, we think we know, is mostly in extrapolation of what we know about more massive galaxies to dwarf regime. So we need more observations. And at the end, I will tell you that how we're going to address this in the future. There will be new observations. So we're going to work on that. And what would be our plans to really start learning more about global clusters of dwarf galaxies? So starting from the why we study this kind of objects, why dwarf galaxies, and why in particular the global clusters. You may agree with me that most of the knowledge that we have about dwarf galaxies comes from this kind of objects. And the most nearby dwarf galaxies that are in our local group, they are too close, at least in my study, they are too close that we resolve all the stars. We can derive the color magnitude diagrams, study star formation histories, star formation rates. We can do a spectroscopy of individual stars, at least the brightest ones. We can measure abundances, chemical abundances. We can measure ages, metallicities, looking at kinematics. Gaia gives us proper motions, so we can model a galaxy. So there are plenty of information we can get out of these most nearby ones. And of course, there are some tens of these kind of objects in our local group. Some of them are shown here. They look quite different from each other. We have objects like Large Magellanic Cloud, which in my definition, it is a massive dwarf galaxy, but still a dwarf galaxy, up to the very faintest ones, ultra faint dwarf galaxies, which by themselves, the whole different field of research. And these properties, the diversity of these properties can be also shown in the scaling relations. For example, what I'm showing here is the half-life radius or effective radius of galaxies versus the absolute magnitude in V-band, which can be a proxy to stellar mass as well, and mass in general. And we see that most of the dwarf galaxies that we are talking about are here within a magnitude like in V-band -16, 17, down to -8, and also sizes of about few hundreds of parsec to 1, 2 kiloparsec. And then we also have ultra-faint dwarf galaxies here that become very much fainter, and also they start to become smaller. Okay, so having this in mind, something that makes dwarf galaxies quite interesting for some of us is the fact that once we look at the fainter ones, we see more dark matter. So this is what I'm showing here. On the y-axis, we look at the fraction of dark matter to a stellar matter. And on the x-axis, again, the V-band absolute magnitude, which is, again, something about how luminous the object is, or how massive in stellar mass the object is. And we see that fainter the objects become, like toward the left, this fraction increases. So it means that we have more dark matter compared to the stellar matter. This is something we also somehow know in other ways, like people try to do kind of abundance matching based on more massive galaxies, a number of them, and halos that we expect from simulation. We do some sort of matches, and people make some plots like this. What I'm showing here is that the inverse ratio here, like this is halo to stellar mass, this is stellar to halo mass, just inverse, versus different halo mass of galaxies. And this is a well-known property of galaxies, that there is a peak around 10 to 12, like our own Milky Way. They're very efficient in turning the mass into stars, but also it drops for more massive galaxies, apparently due to some AGN feedback, and also for lower mass galaxies, for dwarf galaxies. But also you see that there are lots of different ways to do abundance matching, and they start to become very different at the dwarf ratio. So this is a kind of domain that we don't have proper constraints, and we also need to have better measurements of mass. So there are lots of things about this part of the diagram that needs to be addressed. But overall, the behavior, the overall idea here is that these galaxies have more dark matter, right? So because of this idea, all these tensions and inconsistencies that we see when it comes to dwarf galaxies become more exciting. So what I'm saying that, let's say we observe dwarf galaxies in local group, we simulate dwarf galaxies. Well, some people do that, and we compare what we observe and what we simulate. And we see there are differences. There are some consistencies, and also there are inconsistencies. And these inconsistencies are known, some of them known for decades. Some are newer, and I think every now and then we hear about something new. There was a review recently that puts somehow summarized most of these inconsistencies in this table, categorized in different ways. Things like missing satellite problem, which is something most of you probably know about it. They put it as something that it seems that there's not much tension. I mean, I'm not going to discuss that. That's the opinion of the authors. But you get the idea. There are tensions, and we need to understand. Some tensions are weaker, some are stronger, but also there are some uncertainties. But then the question is that because these dwarf galaxies have lots of dark matter, these inconsistencies can be addressed either by changing the baryonic physics or the physics of dark matter, or somehow maybe both. But the problem is that they're highly degenerate, meaning that you can fix some of these issues with changing both of them. So there are lots of different ways to change these properties, and you don't know which change is actually the right one, because you have too many free parameters, and you can do whatever you like. We never understand what is the actual physics behind this, in terms of baryons and also in terms of dark matter. Okay, so that's why many people say dwarf galaxies. But then there's another component of dwarf galaxies that I'm going to focus today. And that's the global clusters of dwarf galaxies. I'm talking about old compact distribution of stars, look like these objects. For example, for Fornax dwarf galaxy in our local group, it is quite well known that it has 5 global clusters, in total 6 star clusters, 1 open cluster, I guess, is one of these. And people have studied this globular cluster now for some time, and including some other dwarf galaxies. We have a few of these globular clusters. But then when we start to look at other environments, things start to change. For example, in more massive galaxy groups, like this galaxy group, or in galaxy clusters, we have denser environments. Lots of other things happen, and they can lead to differences in properties of dwarf galaxies, but also in the properties of their globular clusters, as I will show. Okay, so now for historical reasons, I'm going to tell you a little about kind of galaxies we call ultra-diffuse galaxies. And this is kind of object that appeared in our surveys since maybe 2015 when we started to dig deeper. And you see this kind of objects, as the name says, ultra-diffuse galaxy, they're very diffuse. You can see background object, the light of background objects. Okay. You would see that the light of background objects passing through the galaxy, okay? And if we again come back to this scaling relation, we see that ultra-diffuse galaxies are on top. It means that they have luminosities like dwarf galaxies, minus 15, 16, 14, but size, effective radius that is comparable to Milky Way, like 3, 4 kiloparsecs. I mean, that's what people say. I'm not going to advertise them. That's a whole debate that what are these galaxies. But something interesting, in this plot, which is from 2009, there is nothing there. And we started to find them very recently. So now, if you look at the same plots, you see lots of points as well here. So people start to find these things, and something quite striking in the beginning was the globular clusters. So we had better surveys, deeper surveys. We started to see globular clusters different than before. And there were some objects appear out of the surveys that started debates. So here I'm showing 3 ultra-diffuse galaxies. They're highly debated in the literature. Some like Dragonfly 44, one of the first ones that is studied. There are works that shows the galaxy has like 1,000 times less stars than Milky Way, but it has 100 globular clusters. This is comparable to the Milky Way with 160 globular clusters. So it's like the galaxy is full of globular clusters. But also there are works that shows that this number is actually 4 or 5 times less. It's 20 globular clusters. Okay. There are some little debates about what is the number of globular clusters, but at the end, the galaxy has too many globular clusters for its mass, stellar mass. Also, there is the other galaxy here. Again, there is a debate about how many globular clusters we see. Different works give different numbers, but overall, we see too many globular clusters for its luminosity. And then another galaxy that is also known for some dark matter, blacking dark matter issues, NGC 1052, DF2, which, I mean, regardless of the dark matter properties, if the galaxy is indeed at the distance that people say, like 20 megaparsec, that means that the galaxy has 10 globular clusters as bright as Omega Centauri, which is one of the brightest globular clusters around the Milky Way. So how come the galaxy can have this many bright globular clusters? So, well, I'm not saying I believe in this. I'm just saying that all these led us to think about globular clusters around dwarf galaxies, okay? But something was a bit missing. So now we look at these kind of objects more and more, and also not just UDGs based on what people say, but dwarf galaxies in general. And what we see is that there's a diversity in the population of globular clusters in these dwarfs. So we don't have crazy, extraordinary dwarf galaxies with many globular clusters, but we have a spectrum, and we used to look at the maybe extreme part of the spectrum, but this is more continuous distribution that we see. It is a diversity that we are seeing. Okay, coming back to this, and I talk about this diversity, and I think this diversity is important to explore. But before going there, what we need is to measure this diversity. We don't have enough observations. We need better measurements to quantify this diversity. And for this reason, I normally like to put this diversity in this column. This is something uncertain. We need more data, more dwarf galaxies, and better observations. And I hope that in the future we can address that. At least we need a few years to look at global clusters of dwarf galaxies and make proper measurements. And let's say once it is done, then we can ask ourselves, okay, then we measure this, then what? Then we can come back to these bigger questions that we had, and we can see if this diversity is produced by models that we have, galaxy formation models, let's say out of cosmological simulations. And we can also use these global clusters to somehow break the degeneracy I mentioned before. So I said there are different processes that we can tune, we can change and fix these issues about dwarf galaxies, but each change in your tuning will change the global clusters differently. So you have new set of constraints to see how much this tuning will help. Yeah, so that would be great if we have these cosmological simulations. What we don't. This requires a very, very high resolution, let's say, simulations. We already have problems with making dwarf galaxies, but then global cluster is a thing by itself. But there are works, people start to exploring things that are not necessarily making them inside a cosmological simulations, but somehow taking part of the simulation or taking some overdensity of gas in simulation and use models or models of star cluster formation, or somehow people pack global clusters around galaxies. So people are doing things, tricks that makes things that at least gives us some insights about what is going on. I'm not going through these models, just putting a few of them that have potentials to be used to explore global clusters of dwarf galaxies. But there are more upcoming simulations. Hopefully, once we have good observations, we also have good models. Okay. And once we have these good models, what we do, we start to maybe move this box around. If models that we have for global clusters of dwarf galaxies work or not work. And I personally really hope that one day we're able to move that box there, because this would mean that our models are not great. It means that we will probably learn new things. If we make simulations and everything works well, okay, so nice. But maybe it's better if they don't make sense. That means that, okay, you probably can learn something out of them. It's my personal opinion. I'm not saying it's there, but we will explore and see how it would be. Okay. So that brings me to end of the first part. That is about why we look at global clusters of dwarf galaxies. And just in brief, we can say that, okay, we know all these tensions, problems around dwarf galaxies, but also we know we can already realize that global clusters have additional information to add here that break the degeneracies. We can also test our models further, and for that we need some models, good models first as well. And hopefully, once they are there, we can also start to explore our galaxy evolution models in a different level. Okay. So then for next part, I'm going to tell you more about, okay, now what is being observed and what is known about global cluster of galaxies in general, and then dwarf galaxies. Okay. So before that, let's review a little what we expect, like what we think about how these objects are formed. Like, okay, we have galaxies that will evolve and form and evolve, but what about global cluster? How exactly they end up being around galaxies? And it's a bit complicated question, but just to have a very brief overview, let's say this is a galaxy, right? This is actually what I'm showing is the hierarchical evolution or formation of a galaxy. We have a bunch of different halos. For example, every line is kind of a halo, forming different redshifts, and then they merge. They merge, and they led to some galaxy at redshift 0. Okay, hierarchical formation. And there are at certain points there are star clusters forming. Star clusters that are forming at a lower redshift, at higher redshifts, probably formed in a low metallicity environments, because the universe didn't have enough time to enrich the environment. Also, they were in the lower mass galaxies, so they were become lower metallicity, and then later on they become higher in metallicity. So we have a range of star clusters formed with different metallicities. And at the end, all of them formed quite early on, redshift 2, 3, all of them are quite old when we come to redshift 0. And redshift 0, we see this population of objects around galaxies. Some are a low metallicity, some are a high metallicity. That's why they're like blue and red. So it's a mix of what has happened in the past. Then what formation of these objects aside, these objects also evolve over time. So let's see. I'm going to show something here. So let's say star clusters, once they form, what happens is that they evolve over time. And most importantly, this evolution is about the evolution of stars within them, and also explosion of supernovae is there. Stars inject a lot of energy, and it also changes the dynamics within the system. And then, most importantly, the galaxy itself. So these star clusters are around the galaxy, right? The galaxy itself start to take away some of the stars. So these star clusters lose stars over time. Okay, so this is a simulation that somehow shows this, quite a nice one. And so just before that, just explaining. So the simulation tries to keep all the stars in the simulation within a frame. So you see that it goes back and forward. But look at how things evolve. So there are lots of things that normally happen during the evolution of these objects. So see, now it's zooming. I can start from here, actually. Yeah, so evolution starts. You see things exploding, colors change over time, and the global cluster itself, the distribution of stars changing because of the dynamical interactions with the host galaxy. So there are plenty of different processes involved, and that makes it a bit complicated. Like global clusters that we observe that are formed are not exactly global clusters that we observe now. So that adds another sort of complexity to the whole problem here. So they evolve as galaxies as well. Okay, so this is a very simple way to look at this. And let's now go to observations. And yeah, so when it comes to observations, there have been several surveys. Mostly, they target a certain region of sky, like a galaxy cluster or galaxy group. But there has been also nice surveys with HHT targeting some again nearby galaxies. And these two highlighting here for HHT observation, some surveys for Virgo cluster and Fornax cluster are very valuable in what they told us about global clusters in general around galaxies. But there are more, and there are several ground-based work as well, but nothing really can compete with space-based data. So these two main surveys that I mentioned, the ones with Virgo and Fornax, they are not necessarily about dwarf galaxies. They have all sort of galaxies, and like this is the sample that they use for Virgo survey with HST, and you see all sort of. I did it again, and they show here like the sample. You see all these are very massive galaxies in my definition, and at the bottom you start to get some dwarf galaxies. So it's not dedicated to that, but we can somehow see how like dwarf galaxies, the most massive dwarf galaxies are. So these are space-based observations, so we can also study the global clusters in detail. And so in the next slides, I'm going to show you what we normally find around galaxies. So here, what I'm showing is what we call luminosity of global clusters. So each plot, for example, take one of these plots here. So it says for certain magnitude, certain filter, certain band, for example, Z band, how many global clusters we have in different magnitudes. Okay. And we see that it has a sort of Gaussian shape. So we have these are like brighter global cluster. On the right, you see fainter ones. And you see that we have fainter global clusters up to the peak, and then it's going down. This is something quite well known nowadays, that global cluster luminosity function is quite Gaussian. But we can also characterize this based on the location of the peak, like at what magnitude this happens, and also the width of the distribution. Two parameters to quantify this. And the peak is quite the same, more or less, but we also see slight differences. We see that as we go to lower mass galaxies, the magnitude of this peak also goes slightly lower. So this is a luminosity function, and then it shifts for lower mass galaxies. But you see also it goes to -18, -17 in magnitude. These are quite bright galaxies still. These are not really dwarf galaxies. But for dwarf galaxies, more fainter galaxies, we can say, oh, well, I have this red line, I continue it, extrapolate it, so I will get even low, expectation. We don't have measurements, we can only have expectations. And also there are measurements for width of this distribution. We also see that, okay, the width for lower mass galaxies, the Gaussian starts to become narrower, going down and again, we don't know that after -17 in magnitude. So this shows how limited our knowledge is about anything after -17. Another property is the radial distribution of global clusters. It actually tells us a lot how things are gathered over time by the galaxy. So just let's stick to the one on the left. It shows stellar mass galaxies with different stellar mass, and on the y-axis it shows it demonstrates a parameter we call, let's say, RGC, or GC half number radius. It says how the global clusters are distributed. When this parameter is larger, it means global clusters are everywhere, like more extended around the galaxy. And when it's less, it means more compact. And we see a pattern with mass, and we see that massive galaxies have more extended systems of global clusters because, yeah, they gathered this over time from other galaxies, so it is more extended. Makes sense. But again, when we go to, like, this is, okay, we're talking about stellar mass here. After 10 to 9 and 10 to 8.5, we really don't have much. So what about these objects on the left? Like, it's outside of the plot. What about these objects? Okay, and there are ways people look at these kind of distributions, but for a dwarf galaxy with one global cluster or two global clusters, you cannot really look at the distribution of global clusters. What people do is what we call like stacked radial profile of global clusters. We see how this, for example, here shows us radial profile of global clusters around 70 galaxies. Assuming that all these galaxies are just one galaxy, see how the distribution is overall. So people do this kind of things, measure things, and then that's what we can do at the moment. Okay, I understand it's a lot of information, but there are other interesting things. For example, just very briefly, there is a correlation between a total mass that we find within global clusters and the stellar mass and halo mass of galaxies. Somehow also can be translated to a correlation between number of global clusters and like the halo mass of galaxies. So people say, okay, how many global clusters are around the dwarf galaxy? I use that, I just count them somehow, some statistics involved. And then we can say, okay, this is the range of the halo mass because we expect things to follow this relation observationally. And talking about numbers, people in global cluster community really like to talk about another parameter related to numbers, calling specific frequency, which is number of global clusters normalized to stellar mass. And overall, it has such a behavior like this. You see that, again, for x-axis, we have different luminosities of galaxies. On the y-axis, we have this specific frequency. There is some sort of a minimum here, about -19, and then it goes up both sides. It means that, let's say, more massive galaxies and more dwarf galaxy become, you have more global clusters for a given luminosity. Okay, that's a behavior that actually makes sense to us, because if number of global clusters follows halo mass, that's what you should get. Here you would get, let's say, for dwarf galaxies, you have higher halo mass to stellar mass ratio, then you get more global cluster for stellar mass. So this will go up. What I'm trying to say is that this makes sense to us. Okay. So this simple picture that we have about global clusters and correlations, it also start to make sense when we look at these properties. But still, it's limited for lower mass galaxies. But now here, see, this is another plot like for a specific frequency, but now we're going to lower masses, lower luminosities. But importantly, this is not just any dwarf galaxy. These objects that are studied are these UDGs. So why I'm telling this? The thing is that since people found these UDGs, they started to really look at these objects. So there are lots of observations of certain population of dwarf galaxies and not all. So we have lots of biased samples, in my opinion, of properties of global clusters of dwarf galaxies. They're biased because the sample is biased. And we don't know much about the dwarf galaxies themselves. So it's very hard to interpret these results. For example, here people say, oh yeah, these dwarf galaxies, this red line, this is UDGs, have higher specific frequency than a dwarf galaxy, which are like in blue, let's say the shady part. Like, oh, UDGs have more global clusters. Okay, they do, but our observations of dwarf galaxies are very limited at the moment, and we're looking at very specific samples and environments. Things are more complicated than that, probably. Okay, so just this figure also tries to give the same message that for pink points, so here I'm showing number of global clusters, stellar mass. We see that pink points are like these UDGs, and they are on top of the diagram compared to, for example, this green points, which are dwarf galaxies. But it's a different kind of data set. These purple ones are all based on HSC observations. We have good quality data, but then for green ones, we have ground-based data. The scatter we see is scattered measurements, not scattered in physics of global clusters. So the comparison between these UDGs and dwarf galaxies is it's not easy because we don't have the data. And that's the whole motivation here, to dig into the properties of dwarf galaxies better than before, because then we can have the power to interpret results better and not to have this unbiased picture. Okay, yes, it was quite lots of observations, and believe me, I try to keep them as small as possible and focus on the main ones. But there are more properties of global clusters that people can explore. There's a lot of things about cell populations, as for example. But overall, what we learn about from these slides, and as I like answer for the second question, is that somehow what we know about dwarf galaxies and the global clusters is not exactly what we know. Is extrapolation of what we know about more massive galaxies. We see massive galaxies behave like this, then we go to dwarf galaxies, it should become like this. And then there are some observations of some dwarf galaxies, but these are the UDGs that I'm talking about, and these are quite biased sample. So we have some sort of a very patchy knowledge when it comes to global clusters of dwarf galaxies. We have information of certain parts, but not everywhere. So without having a puzzle complete, we cannot really say much about the whole picture. And that's the whole thing we want to tackle in the next part by talking about, okay, then what? There are things we don't know, we don't measure, we haven't measured properly, then what we can do and what is the plan? Okay. Okay, now we want to understand, so what we should do now, how can we have better measurements of dwarf galaxies and their global clusters? So understanding this also means that we should understand why we couldn't have this before. Before we had, for example, something like this. We had a dwarf galaxy. It's a ground-based observation, 8-meter telescope, is super deep, but you see all these little points around it. The question is, are these like global clusters around the galaxy? We don't know. There might be some background stars. You see there are dots everywhere. Not everything is a global cluster. Some are global clusters, but not all. Well, if you have the infinite time in the universe and the best telescopes, you can do a spectroscopy for almost everything there and see what is the radial velocity. If it matches the radial velocity of the galaxy, you can say, okay, this point source is probably around the galaxy, probably it's a global cluster. But we don't have that. It's really inefficient for You might do that for few galaxies, but not for larger samples. That people, what we do is we stick to these images. We try to do our best observations with different filters. Try to make good measurements, to measure the sizes of these little points, to measure the colors, and some sort of say, okay, which ones can be a global cluster, which ones cannot be. But that is quite tricky, especially when you go further and further, it becomes harder and harder. One solution, as I also mentioned, HSC is great. It's because with HSC, you get high resolution images without the atmospheric limitation. And you can really start to see, okay, some of these objects look like a global cluster because you have better resolution, you have better measurements of size. On top of that, if you have a space-based telescope like HSC, if you combine our traditional optical images with, for example, U-band and K-band, here I'm showing a color diagram, including U-band and K-band, and some optical, another optical filter in between, we start to see that stars, galaxies are quite separated from global clusters. The scatter here is photometric, it's from measurements, but better measurements you get, this becomes tighter and tighter. Without U-band and K-band, what you would see is just everything is on top of each other. Okay, so if you have infrared and if you have U-band, it would be great. So most of these things that I said, like space-based observation and near infrared and maybe U-band, is actually something that we might have very soon. And that's special thanks to Euclid. I'm pretty sure that you are very familiar with Euclid, but just to make sure that we are on the same page and about Euclid, it is in space now, is observing at the moment, and the task is to observe about 1/3 of the whole sky, which is what we call the extragalactic sky, in 6 years. So in 6 years, we have high resolution space-based observations of this area. In addition to that, it has it has several filters. I'm showing here like filters based on the wavelength. So it has a visible filter, very quite wide, and it has 3 near infrared filters. So that is the near infrared information that would be also helpful. So we have high resolution, we have also near infrared images, and a telescope is half size of the HSC, but the quality of the construction is very high, and it can give us data that is comparable to HSC. And just think about HSC is there for 30 years and is still observing, and Euclid will be there for 6 years and observe 1/3 of the whole sky. That's crazy. And this 1/3 is what I'm showing. Well, this figure shows in green. Okay, so we have this great spatial resolution of Euclid. We have the large sky coverage that we estimate we will get data of about some tens of thousands of dwarf galaxies in our local universe, like within let's say 50 megaparsec. This is the distance we care about, because this is where we can also detect the global clusters. But that's a lot compared with the few hundreds that we have already. We'll have tens of thousands. And we have near infrared photometry, and also we have optical photometry. This also includes something that people normally forget. The data of Euclid comes with some ground-based data. It is not necessarily part of, it's not a survey that we call Euclid, but this is like external data that will be provided for Euclid. There are people working separate in the consortium. They are working on data that is being observed with CFHT, with Subaru, and with pan-stars in different bands, and they're trying to do re-reduction. They're trying to do recalibration and to give us very well photometrically calibrated images in UGRIZ. So with all this, we can really start to find global clusters around all these dwarf galaxies that Euclid will observe. Okay, that's great. And actually that's why I'm here. I'm invested in Euclid, because this is like the perfect combination that would work for me. Of course, it's not only one. There are other surveys coming. LSSC has deeper data, but in 10 years, it has U-band as well. It's great, but also data rights are something else. So we always, as astronomers, more about, okay, what we have access and what is the best. And for Euclid, there are some models, some simulation that shows that the fraction of global clusters that we detect at about 20 megaparsec is like about 100%. Why I'm talking about 20 megaparsec? It is quite of a, I say, very interesting distance for people like me. There are two nearby galaxy clusters, Fornax cluster and also Virgo galaxy cluster. They are at 15, 20 megaparsec. Fornax is part of a bigger supercluster, which the whole thing is at 20 megaparsec. So we have a big structure with different environments at 20 megaparsec. So if things work at 20 megaparsec, I'll be very happy. Of course, we can't go further and further, but we start to lose some global cluster because we stop detecting them. Okay, so data of Euclid will come in a year if you're part of consortium, which you can be. But we already had some early release observations, and there are 17 targets that have been observed with Euclid. Okay, and people here have been involved as well. I'm very briefly going to tell you about a few of them. That's a few targets that can give us something about global clusters of dwarf galaxies around the topic of this talk. That they come from three main programs. We're looking at nearby galaxy clusters, some program for Fornax cluster, and some for the Perseus galaxy cluster. So we have data of two local group B, let's say, dwarf galaxies, NGC 6822. There are works looking at the star cluster around them, comparing them with what is known already before. There are new candidates as well. There are also candidates that reject, like global cluster that are rejected as being as global cluster. Also, there's another one, IC10. This is another dwarf galaxy that Euclid has observed, and people look at the star clusters. And what we learned from these most nearby ones is actually stellar populations. I didn't talk about star populations in global clusters, but this is very essential kind of information as well. And we see that if we combine infrared photometry of Euclid, Y minus H, for example, with some near like ground-based data, we can start to see like different curves for different ages and metallicities. That normally this would be like you see things for certain metallicity here at different ages. If you do a star population, you're familiar with this kind of plots. If you don't have near infrared and not combined with optical, it will be on top of each other. So with this kind of information, we can say that global cluster has this age and this metallicity. We break the age metallicity degeneracy. There's another one about outside of the gold group, about 3 megaparsec from us. It is still at a distance that's it is still at a distance that we start to resolve the global cluster. We see that okay, these are like star cluster, which is great. But then we go to 20 megaparsec, things become different. We had a little field in the center of the Fornax cluster. This is the center of the Fornax cluster. This field is part of it. It has 10 massive galaxies, but about 30 dwarf galaxies. Lots of global clusters that are already known. So we could test things, and we did, and things seems that works. So this 20 megaparsec distance, we also have tests for it. So things look like what we expected. And of course, given that resolution that Euclid brings for us compared to some ground-based survey, we're not really surprised. So we really can see things that like details that we couldn't see before for this large number of objects at once. Then another one that I mentioned was the Perseus cluster. It is about 70 megaparsec. It's further global cluster of points. But just compared what Euclid has covered in one exposure, this is like the lighter gray area. And what HST has observed, this is like this squares, gray squares on top of it. This is what HST has observed over 30 years in different programs. In one shot of Euclid, we have all this information, and we could observe about more than 1,000 dwarf galaxies. This is incredible, and this is also important because this is not a really biased sample. We look at properties of these objects. We have all sort of dwarf galaxies. This is what we wanted, right? In the past, people look at certain groups, certain UDG-like or this kind of dwarf galaxy that have this property, but now we have everything. It's the most unbiased sample that we have. And for that, we can start to look at different properties of global clusters. This is some work of mine going on at the moment. We look at these properties, how it changes with different properties of galaxies. We can start to look at trends. For example, finding trends based on different surface brightness of galaxies. I'm not going to really talk about it, just to present that we are starting to get information that was not possible before. Okay. And that is all due to this data set that we have. Okay. I'm coming back to this plot again, showing the coverage of Euclid. I talked about all these EROs, but over 6 years, Euclid will observe this area. And now I talked about part of the Fornax cluster and Perseus galaxy cluster, but then we have more nearby systems as they will observe with Euclid. I think these names are quite familiar. And on top of that, we also have lots of dwarf galaxies which are not in clusters, they're just in isolation. And we can also explore their properties. So there's a lot to do here, and we can see how global cluster properties of dwarf galaxies changes with the properties of galaxy itself and the properties of the environments. So that is something we never had, and we're going to have just in some years from now. Okay. So that somehow brings me to the end of this part to answer this question that, okay, then in the previous part we said that we lack observations, then what we can do? What we can do is that, well, things are already prepared. There's a space-based telescope there. We need to use it in a most efficient way to observe all these dwarf galaxies. We already know from early release observations that things that we predicted is actually what is going to happen. We know things are going to work, and we're trying to plan for upcoming data of Euclid. For example, data release 1, which for us it will be a year or 2 years, let's say, if you want to use the public data, and there will be 2,500 square degrees of sky, and that is huge. So we're also dealing with this, lots of technicality to deal with. Okay, so this is actually the take-home messages that I want to leave you with. So I hope it is the main message is clear. It's mostly about that we have questions on dwarf galaxies, and global clusters can potentially solve these questions, but we need good observations. We need also good models. Models hopefully come, but from the observation parts, we can do something already now. We can we already see that there are certain properties that we expect by looking at more massive galaxies, and we start to see things about dwarf galaxies. It's not enough, but then with Euclid, we can go to the next step. We can really look at a large number of galaxies, different properties, different environments, and see how things are for this regime. And then once we have answered to this, we can come back to models and try to see what these models say compared to observations that we have. This is a long-term plan. So let's say, hopefully, if 5 years from now I'm invited here, I hope I don't repeat this kind of things, and there'll be, a next stage that I will talk about. So yeah, and lastly, I just want to, there are like a couple of minutes. I like to show a video that that ESA recently released. It's like a PR kind of video to show the amazingness of data of Euclid. It's 1% of the Euclid data that will be released eventually in 6 years, and presents how much detail is here. So yeah, I'm going to set up something and then play the video. I think it's ready. So. Yeah, I mean, the main message is, thank you.